So now we have this thing, right, called de Moivre's theorem, is the gentleman's name. And what it's going to do for us is it's going to give us a way to very quickly evaluate complex numbers raised to powers, including fractional powers, right? So it's also going to give us a way to do roots of complex numbers, right? And the formula looks like this, right? And all this is saying, right, is if I've got a complex number and I write it in its polar form, right, r cosine theta plus I sine theta to the n. Then to simplify this, I just raise r, the radius, to the power and multiply the angles by n, right? That's it. All right, so let's look at an example. All right, first I have to rewrite this as in its polar form. So r is the square root of the square root of 2 squared plus the square root of 2 squared. That's the square root of 2 plus 2. That's the square root of 4, which is 2. And theta is the inverse tangent, negative square root of 2 over the square root of 2. That's negative 1. And the inverse tangent of negative 1 is negative pi over 4. Now, I'm fine with getting a negative angle here. Okay, so that means my number here, this is 2 cis negative pi over 4 to the 8th. And to simplify this, I raise 2 to the 8th power, and I multiply the angle by 8. Cis negative pi over 4 times 8. So this is 2 to the 8th cosine negative 2 pi plus I sine negative 2 pi. Cosine of negative 2 pi, that's 1. Sine of negative 2 pi is 0. 2 to the 8th is, let's see, 2 to the 6th is 64. So this is 256. 1 plus 0i, this whole thing is just 256. And there you go, that's my answer, without all the pain of trying to multiply this out. So how about if we have a fraction, or a fractional exponent? Well, I know it looks a mess, but look, it really is saying the same thing, right? Only now, because when you multiply by 1 over n, you're making the angle smaller. So we have to deal with that whole plus 2k pi thing, right? And that's all this bit is saying, right? This is saying that this is really rn to the cosine theta plus 2k pi divided by n plus I sine theta plus 2k pi divided by n, right? And the version up here, it just kind of split the fraction up into two parts. So in practice, what you're going to do is you're just going to keep adding. You're going to do 2 pi over n, 4 pi over n, 6 pi over n, right? You're going to let k be 1, 2, 3, 4, and so on until this thing that you're adding here makes it up to 2 pi. As soon as it makes it up to 2 pi, then you're starting to repeat. Okay, so now this is going back to my original question, right, from the previous lecture. How can we find all 4 fourth roots of 1? Right, so I want to evaluate 1 to the 1/4. All right, well, here's how I'm going to do this. Right, I'm going to use my formula here. I'm going to write 1 in its polar form. 1 is 1 plus 0i. Right, so this is, let's see, r is the square root of 1 squared plus 0 squared, which is 1. And theta is the inverse tangent of 0 divided by 1, which is 0. Right? It's the inverse tangent of 0, which is 0. Okay, so that means my number here is 1 to the 1/4 cis 0. And I'm going to go ahead and put this plus 2k pi here to the 1/4. Oops, sorry, I got ahead of myself. Just 1 cis 0 plus 2k pi to the 1/4. Now use our formula. Right? This is 1 to the 1/4 cis 2k pi times 1/4, which is 2k pi divided by 4, which is 1 to the 4th. That's just 1. So this is cis k pi divided by 2. All right, so how do I turn this into actual numbers? Right. Well, to do this, pick numbers for k. When k is equal to 0, this is cis 0 pi over 2, which is 0. So it's cosine 0 plus I sine 0. And let's see, cosine of 0 is 1. Sine of 0 is 0. So that's just 1. Good. I expected that. I already knew that one. Right, now let's keep going. Right, let k equal 1. And we get cis pi divided by 2. So that's cosine pi over 2 plus I sine pi over 2. Cosine pi over 2 is 0. Sine of pi over 2 is 1. So that's just I. Okay, check that real quick. Check that. Is I to the 4th actually 1? Well, yeah, it is. Excellent. That works. All right, now let's try another one. Keep going. Let k equal 2. Then this is cis pi, which is cosine pi plus I sine pi, which is -1. -1 to the 4th. Yeah, that's 1. Yes. When k equals 3, we get cis 3 pi over 2. So that's cosine 3 pi over 2 plus I sine 3 pi over 2, which is, let's see, cosine 3 pi over 2 is 0. Sine of 3 pi over 2 is -1. So that's negative I. Check it out if you like, right? Negative I to the 4th is 1. Now let's see, k equals 4. That is cis 2 pi. Okay, stop. Cosine of 2 pi and the sine of 2 pi, those are the same as cosine and sine of 0. See, this is what I was talking about. This is the point where we started to repeat, right? So this is where you stop, and these 4 numbers are it. And that's what we expected. We expected there to be 4 numbers, right? 4 fourth roots. So yeah, that makes sense. In fact, when I'm doing this, I don't really worry so much about seeing that 2 pi gives me the same numbers as 0. I know I'm expecting 4 answers. So I'm going to do 4 values of k, 4 consecutive values of k, and that should give me everything. Okay, so first, you notice what I've done here. I'm no longer limiting myself when I'm talking about polynomials. I'm no longer limiting myself to real coefficients, right? I have a polynomial equation here, and it has complex coefficients. I'm saying find the solutions to this equation, right? Well, see if you can do this yourself, right? See if you can work this out. Then start this back up, and we'll do it together. All right, so I want the solutions to this equation. Well, look, we can solve this in kind of the obvious way, right? Move the 2i over. X to the 3rd equals -2i, which means x is the cube root of -2i. So what I'm really asking for here is what are the 3 cube roots of -2i? I don't know. Let's make this into its polar form, right? R is, well, first, just so we're clear, z is 0 minus 2i. So r is the square root of 0 squared plus minus 2 squared, which is 2. And theta is, let's see, it's inverse tangent negative 2 divided by 0. Okay, well, that's undefined, right? But I'm okay with that. The tangent of what angle is undefined? Well, it's negative pi over 2 and positive pi over 2. Negative 2i, that's, if you were to graph this, it would be the point 0 comma negative 2, which is down on the negative y-axis. So I'm going to use theta equals negative pi over 2 as my angle. Okay, so then this is 2 cis negative pi over 2 plus 2k pi to the 1/3 power. Now, in my experience, it's easiest if you go ahead and find a common denominator and just add these two fractions together. All right, so I'm going to make this 4k pi over 2, which means this is 2 cis negative pi plus 4k pi over 2. And now we'll do the 1/3 power. Excuse me, it's the whole thing here. So this is 2 to the 1/3 cis negative pi plus 4k pi over 6. Now we pick numbers, right? When k is equal to 0, this is 2 to the 1/3 cis. The 4k pi part becomes 0, so this is negative pi over 6. When k is 1, it's 2 to the 1/3 cis, let's see, minus pi plus 4 pi is 3 pi. So this is 3 pi over 6, which is pi over 2. And when k is equal to 2, that's 8 pi. So it's minus pi plus 8 pi. It's 2 to the 1/3, 7, excuse me, got a little messy. 7 cis, 2 to the 1/3, cis, 7 pi divided by 6. There we go. Okay. Now, and I mean, we can do these. This is 2 to the 1/3 cosine negative pi over 6 plus I sine negative pi over 6. Pi over 6, that's 30 degrees. So this is 2 to the 1/3 square root of 3 over 2 minus 1/2 I. This one is, let's see, 2 to the 1/3 cosine pi over 2 plus I sine pi over 2. Cosine pi over 2 is 0. Sine of pi over 2 is 1. So this is 2 to the 1/3 I. And you can do the same thing on this next one. We know it's 7 pi over, well, now that I've started, I can't stop, right? Sorry. This is 2 to the 1/3 cosine 7 pi over 6 plus I sine 7 pi over 6. So that's 2 to the 1/3 cosine 7 pi over 6. That's negative square root of 3 over 2 sine 7 pi over 6. That's negative 1/2 I. There you go. Just couldn't let it go. There's our third one. Okay, now I want to make a quick point about this because these are actually some kind of interesting results. If we graph these polar numbers, right, what happens? Well, we have negative pi over 6. That's down here. Negative pi over 6. Then we have pi over 2. That's up here. And then we have 7 pi over 6. Well, 7 pi over 6, that's pi plus pi over 6. So that's going to be here. I want you to notice the symmetry here, right? These lines, we're talking about a third root, and these angles divide the plane evenly into thirds, right? Which is just kind of an interesting result. This is this here, the angle between these two dotted lines. It's 120 degrees here. It's 120 degrees here, and 120 degrees here. These complex roots, they're always kind of uniformly distributed around a circle this way.